5.1 talks about eigenvalues and eigenvectors. The use of eigenvalues and eigenvectors we'll talk about later on. For now, let's talk about, well, what are they? An eigenvalue is just a constant, nothing more. We refer to the eigenvalue as lambda. The eigenvector is an actual vector. So, you know, vectors and constants, you can't mix those. So an eigenvector would be a vector that corresponds to this lambda. And that is the vector x such that if I multiplied a matrix times that vector, it's the same thing as multiplying a constant times a vector. And do you see the significance of that? So let me start with the definition, which says, if A is an n by n matrix, so A has to be a square matrix, then a non-zero vector, x equals 0. So if I told you, hey, solve that equation, if you say, let the vector be 0, that's the trivial case. We all know that. You didn't say anything. So we want the solution to this equation that does not have x being 0. If this is an n by n, then x must belong to r sub n. So it must be 1 by n. It's called an eigenvector. So this x is called an eigenvector of A, of this matrix A. Or the matrix operation T sub A, which is, you know, just the linear transformation. If AX is a scalar multiple of x. So I take A, this matrix A, which consists of vectors, I multiply it by this vector x, and that's the same thing as taking that same vector x and multiply it by a scalar, a constant. For some scalar lambda, the scalar lambda is called the eigenvalue of A, and x is called the eigenvector corresponding to this lambda. Now, the idea might seem a bit off in the beginning, but since we're going to do this over and over and over in 5.1 and 5.2, you'll get the hang of this, not that hard. And a couple of more things to talk about. Now this I'm going to show you. So solving this, given A, finding lambda and x so that this is true, that's a lot of work. Instead, they take ax minus, actually they went the other way. Okay, that's fine. You know, solving an equation, you could put everything on the right, you could put everything on the left. Solving ax equal lambda x, I could say 0 equal lambda x minus ax, or simply 0 equal x into lambda I minus a. And we already know x cannot be 0. It must be that this is 0. This is also a lot of work. I'll show that as well. Somebody figured out, instead of solving this equation or this equation, it's sufficient to take the determinant of lambda I minus a equals 0, solve for lambda and find the eigenvalues, instead of doing this. And again, I'll show that as I do an example or two. Here it says the same conditions. If A is an n by n matrix, lambda is an eigenvalue of A, if and only if it satisfies that the determinant of lambda I minus A, other books have it A minus lambda I like it like this better, equals 0. Excuse me. Okay, this is called the characteristic equation of A. This is called the characteristic equation of A. It's going to be in terms of lambda. And we'll talk about that when we get there, which is in a couple of minutes. Theorem 5.1.2 pretty much says what you already know. If you have a square matrix, and that square matrix is triangular, whether it's upper triangular, lower triangular, or just diagonal, then the eigenvalues of lambda are the entries on the main diagonal. Right? Remember, if we have lambdas, you know, by this equation, I'm sorry, not a matrix. it could be upper, or the zeros could be here or both. It doesn't matter. Remember, the determinant of this will be the product of those. And if you set them equal to 0, then the eigenvalues, which is the solution to that, will be the main entries on the main diagonal. We'll talk about that again. I'll point those out as we go on. That's something that we know. This is something that is an added bonus for it. If you have a square matrix, which means A is n by n, then the matrix is invertible if and only if lambda equals 0 is not an eigenvalue. So if you find the eigenvalues of any square matrix, if lambda doesn't equal 0, then that is an invertible matrix. Now let me elaborate here really quick and show you the very first case. Here they're saying confirm by multiplication that this vector is an eigenvector of A. Find the corresponding lambda. Now, this might seem like a bit confusing, but since we're going to do this over and over, it's really simple. We're going to always come back to that. AX, we know what AX is. That is 5, negative 1, 1, 3, 1, 1. That is 5 minus 1, and that is negative 1 plus 3. That would be a 4, 2. Oops. I see, I'm not sure I put a negative there. That is 1 plus 3, that's 4. So this is AX. And we want it to equal some multiple of 1, 1. And what do you think that is? So what do you think lambda is? Lambda must be 4. Lambda equal 4 is an eigenvalue. And this vector, 1, 1, is the eigenvector of A corresponding to lambda equal 4. So for now, they're giving you the problem and the answer. Pretty soon, they're just going to give you the matrix A. You have to find that lambda, and you have to find that vector, so that when I take this matrix A, multiply it by this vector that I'm going to find, I'll get lambda times the vector. And there's a really important reason why they're doing that. We'll elaborate on that a bit later. Same deal here. They gave you the eigenvector. They're saying find lambda. Well, it's simply AX one, 1, 1 makes it really simple. What is that? That is 2 minus 1 minus 1. That is negative 1 plus 2 minus 1. And that is negative 1, negative 1 plus 2. 0, 6, 5, and 0, if I'm not mistaken. Never mind. That's a negative 1. That is 0, 0, 0. So this is AX. I'm going to set that equal to lambda times. And what do you think lambda should equal so that those two are equal? So we're solving this equation. Well, doesn't that indicate that lambda must be 0? So the lambda equals 0 is the eigenvalue, and x equal 1, 1, 1 is the eigenvector corresponding to lambda equals 0 for matrix A. Again, pretty soon they're going to give you A and they're going to say, find the eigenvalue and eigenvector. Find me a vector so that when I multiply this matrix A by this vector, I'll get lambda, which is a constant, times that vector. So you're going to find both. And here we are. Now, find the characteristic equation the eigenvalue, and the basis for the eigenspace of the matrix. It sounds a lot more complex than it really is, something that we did over and over and over. Let's get that out of the way. So initially, we were supposed to say, look, and I'm going to do this the long way. So initially, we were supposed to say, this is matrix A, take AX and set it equal to lambda x. And that's going to be 2, 1, 1, 2 times x1, x2. And that's not what they mean by, that's not how we're going to do it. We're going to do it using the shortcut. But for now, let's do it the long way. Let's just make sure we grasp where does this come from. So for now, we're doing this. That's how they did it first. And if I look at this, well, hey, that is a 2 by 1. That is 2x1 plus x2. And that is x1 plus 2x2. And that equals lambda x1 and lambda x2. And that would mean that 2x1 plus x2 equal lambda x1, and x1 plus 2x2 equal lambda x2. And I could say 2, I could do it right or left, it doesn't matter. I could do 2x1 minus lambda x1 plus x2 equals 0. And I could do x2 minus lambda x2, apologies, that should be x1, right? That's x1 plus 2x2. So that should be, when I move this over, that should be x1 plus 2x2 minus lambda x2 equals 0. Now, if I look at this and I say, well, look, can't I say this is 2 minus lambda, 1, 1, 2 minus lambda, 0, 0, right? And can't I say now, if I take negative 2 minus lambda, oh, they happen too much, 2 minus lambda times row 1 times row 2. Add it to row 1, put the result in row 2. Again, we don't do that, but multiply this by so that makes this negative 2 minus lambda plus that, that's 0. And if I take this multiplied by this, I'll get, so here, let me write it out. I'll get negative 2 plus lambda for this piece. And here I'll get negative 2 minus lambda squared, yeah? And that's a 0. If I add it to 2 minus lambda, 1 and 0, I'll get 0, 1 minus 2 minus lambda squared, and a 0. So, doesn't that mean that this times x2 equals 0, right? Now we know x1, x2 can't be 0. This vector can't be 0. So if I take 1 minus 2 minus lambda squared, set it equal to 0, I'll get 1 equal 2 minus lambda squared, 2 minus lambda will equal plus or minus 1. And I could say that if I swap those, lambda equal 2 minus or plus 1, lambda will equal 2 minus 1, which is 1, and 2 plus 1, which is 3. Now, did you see all of that work that we did? If I take the determinant of lambda I minus a, if I take the determinant of lambda I minus a and set it equal to 0, that would be, and again, this step right here, we're not going to write after that, we'll jump straight to this step right here. That would be the determinant of lambda I. For a 2 by 2, I is minus a, and what would that be? That will be lambda minus 2, 1, negative 1, and negative 1, and lambda minus 2, right? Again, no need to skip a step. I'm going to show everything. That would be lambda 0, 0, lambda minus 2, 1, 1, 2, and that would be lambda minus 2, 0 minus 1, 0 minus 1, and lambda minus 2. That would be all of that work. If I take the determinant of that, that's simply the determinant of listing those in. Isn't that, oh, if I take that and I set it equal to 0. So this determinant would be lambda minus 2 squared minus 1 equals 0. And do you see that if I would have jumped from this to the straight, I would have saved myself, excuse me, all of this and got it down basically to this step. I'll move the one over. Lambda will equal a 3 or a 1. Now, what do you do after that is the same for both. It doesn't matter. But the key is for us to work, instead of solving this, which is a lot of work, we're going to be solving this, and that's going to give us the eigenvalues. Now, we're going to do this on almost every problem in 5.1 and 5.2. So, now that I showed you, I said I was going to show you in the first example, and here it is. If you glance at this, instead of doing this lengthy method, let me reboost or restart that problem one more time. It didn't. Okay. So let's restart the problem one more time, and let's restarting fresh. Direction says find the characteristic equation. By the way, the characteristic equation is really solving this right here. Pretty much solving that. So find the characteristic equation, find the eigenvalue. Once you find the eigenvalue, you're going to find the eigenvector, and that's going to form the basis for the eigenspace of the matrix. So let's start over again fresh. Now, we're not going to do this the long way. We're going to say, look, this is matrix A. And if I take the determinant of here they put backwards. Lambda I minus A. Most other books put A minus lambda I. It doesn't matter. Remember, for a 2 by 2, this is simply 1, 0, 0, 1. If you multiply it by lambda, those are lambdas, minus A, wouldn't that be simply? So this minus A, that will be 2 minus, backwards, that will be lambda minus 2. Yeah? So here, put them together again in the beginning, just until you get the hang of this. So this minus this, 0 minus 1, 0 minus 1, and lambda minus 2 equals 0. Isn't that the product of those? Minus the product of those. And we agreed that lambda minus 2 squared. Actually, I could even factor that. Anyway, let's just go ahead and do it. Lambda will be 2 plus or minus 1. Lambda will equal 3 or 1. So characteristic equation is pretty much this. Eigenvalues are right there. That's like A and B. Now comes the busy work. And what is the busy work? Well, finding the eigenvectors. If I take lambda equal 3, now it's important that you keep track of what is what. If I take lambda equal 3, then I'm looking at ax equal 3x. Well, I know what a is. A is right there. If I take ax equal 3x, wouldn't that mean that I'm solving the augmented matrix? Ax minus 3x equals 0. Or simply a minus 3i x equals 0. We know x cannot be 0. So a minus 3i, well, let's see. Lambda equal 3 is right there. If I put the 3 there, what would that be? Or here, let me continue. A minus 3i, that's 2 minus... Oh, again, I'm sorry, I apologize. In the previous books, they solve it always this way. This book does lambda I minus 3. So what they do, they move this to the right instead of the left, which is the same idea. Let me write it down so it matches this book. I apologize. So wouldn't that mean 0 equal 3x minus ax? Or I could say 0 equal x into 3i minus a, right? Now, isn't this a matrix times x1 here? Isn't this really x is x1, x2 multiplied by this matrix, and that is 0, 0, because that's the 0. And what's 3i minus a? Well, that is 3003 minus a, 2, 1, 1, 2. 3 minus 2 is 1, negative 1. 0 minus 1 is negative 1, and 3 minus 2 is 1. Or if I just take lambda equal 3 and I put it in there, 3 minus 2 is 1, negative 1, negative 1, 1. Do you see I get the same result? Again, no need to do any of that. So, my work, instead of doing all of this part, instead of doing all of this and all of this, and setting all of this equal, look how quickly I can skip all of that. I could figure out the determinant of a minus lambda I, get the characteristic equation, get the eigenvalues, let lambda equal 3, plug it in there, and solve this. If I take row 1 plus row 2 in row 2, what would I get? That means x2 is 3. Yeah? And doesn't x1 equal x2? So lambda equal 3 correspond to the vector 1, 1. And lambda equal 1, the other eigenvalue. Instead of doing all of this again, just plug it in and solve negative 1, negative 1, negative 1, negative 1, 0, 0. Take negative row 1 plus row 2 in row 2. That means x2 is 3, right? And isn't x1 negative x2? So the vector there is negative 1, 1, corresponding to lambda equal 1. And this would be the basis for the eigenspace corresponding to lambda equal 3, and this would be the the basis for the eigenspace corresponding to lambda equal 1. Or simply, this is the eigenvalue and this is the eigenvector corresponding to that. These vectors form the basis for the eigenspace. Eigenvalue, eigenvectors. They're linearly independent and they form basis for the eigenspace. And that's pretty much what we're going to do for a while. Now, the first couple of examples are always the messiest, but we'll get the hang of this. So again, I've been doing this for a while. I'm so used to the determinant of a minus lambda I equals 0, but it's better the way the book does it here because you always get lambdas to be negative. This is A. They want us to find the eigenvalues and eigenvectors. To do that, we start with find the determinant of lambda I minus A and set it equal to 0. Lambda I, that's a lambda minus this and a lambda minus this. The determinant would be simply lambda minus 2, a negative 3, and a 0, and a lambda minus 2. You set that equal to 0 and you solve it. And that's going to give you the eigenvalues. Now, when you get this out of the determinant, that is lambda minus 2 squared minus 0 equals 0. This is called the characteristic equation. And once I do that, I say, okay, well, let's see. Lambda will equal 2. I'm only getting one eigenvector. So if I take 2 and I put it in there, I'm looking at 0, negative 2, negative 3, 0, 0, 0, 0. Well, what does that mean? That means that x1 would be 3. And x2 would be, so x2 equals 0. This will be the eigenvalue corresponding to this eigenvector, and that forms basis for the eigenspace. And that's pretty much it. So, idea is simple. Where does that work? Well, all of chapter 5 deals with the outcome of this. And how about this problem? Same deal. We take the determinant. Again, this is a shortcut. Determinant of lambda I minus A and set it equal to 0. That would mean simply lambda minus 2 and a 0 and a 0 and a lambda minus 2 equals 0. And the same as the previous problem. This is lambda minus 2 squared equals 0. Lambda will equal 2. So if I put a 2 in there, I'm looking at the following augmented matrix: 0, 0, 0, 0 equals 0, 0. Well, here, this is already in reduced to echelon form. And if I look at this, x2 is free and x1 is free. So I could say 1, 0, 0, 1. That will correspond to lambda equal 2. And those form bases for the eigenspace. Now, what does it mean when you get one eigenvalue? And what does it mean when you get two eigenvalues? We'll talk about what that means and when are you supposed to get the same amount or not. Let me just readjust the problems. Here is another problem. This is A. So if I take the determinant of lambda I minus A, set it equal to 0, that's simply lambda minus 1, lambda plus 1, and the opposite of those, since you put a negative in front of A, set that equal to 0. What do you notice? That would be lambda minus 1 times lambda plus 1 minus and plus 4 equals 0. That is lambda squared minus 1 plus 4 equal to 0. So that's lambda squared plus 3 equal to 0. And that would mean we have no real eigenvalue. For now, that's what we're going to do. Now, in this class, we're going to only cover section 5152. 5.3 deals with complex eigenvalues, and 5.4 deals with that as well. 5152, we don't deal with complex eigenvectors and eigenvalues or how the solution look, and they're not going to give us those. But if we come across a complex eigenvalues, we just simply say no real eigenvalues and just move on. Now we want to do the same thing, and these matrices are handpicked where, and specific in this section where things are going to work out a bit nicer than the tradition. Find the characteristic equation. Characteristic equation is simply you solving determinant of lambda I minus A and set it equal to 0. If I do that here, lambda minus 1, lambda, and lambda minus 4 will be across the diagonal. Multiply all the rest by a negative 1. That's the determinant that you're trying to solve. And you could easily see in this case, if I pick the middle row or column makes no difference. So if I take the middle row or column, set that equal to 0. Wouldn't that simply mean take that lambda, and you have lambda minus 1, 2, 2, lambda minus 4 equals 0. So that's lambda into lambda minus 1, lambda minus 4, minus 4 equal to 0. A bit of algebra. That's lambda into lambda squared minus 5 lambda plus 4 minus 4 equal to 0. So simply lambda times lambda into lambda minus 5 equal to 0. So we have lambda equals 0 and lambda equal 5 being our eigenvectors. Now, characteristic equation, I keep on forgetting. In order, find the characteristic equation. That's the characteristic equation. Find the eigenvalues. Here they are. Find the bases. Lambda equals 0. Put 0 right there. And solve that augmented matrix. Negative 1, 0, 2, 0. 0, 0, 0, 0, and 2, 0, negative 4, 0. Right? Now, again, I don't have to write that anymore. You know how that goes. So if I take twice row 1 plus row 3 in row 3, what would happen? What does that mean? That means x3 is free. Let's start from it this way. And x2 is free. And what is x1? Isn't x1 negative 2x3? So for this, I'll get 0, 1, 0. And for this, I'll get negative 2, 0, 1. Those two vectors will correspond, those two eigenvectors will correspond to lambda equals 0. Those form the basis for the eigenspace. And if I take the second value at lambda equal 5, if I take lambda equal 5 and put that right there, that would be 5 minus 1, which is 4, 0, 2, 0, and 0, 5, 0, 0, and 2, 0, 5, 1, 0. And do you notice if I take negative 2 row 3 plus row 1, put the result in row 1, what would happen? Wouldn't I get 4, 0, 2, 0, 0? That's okay, leave it as 5. You could make it a 1, 0, 0, 0, 0. So what does that mean? That means x3 is free. x2 is 0. And for x1, so that is x2 divided x3 divided by 2, and it's negative. I don't know why I squished that in this small space. I have all the space in the world. So what would be the eigenvector associated with lambda equal 5? With lambda equal 5, what would this be right there? That should be negative 1/2, 0, and 1. Most books will write negative 1, 0, 2. Again, it doesn't matter. Either of those will do. That would be the basis for the eigenspace. And there they are. You can't have more vectors than you have lambdas. That's not possible. Here's another problem. Again, we need to practice this over and over. Number 10 is next. Well, again, find the correct equation. Determinant of lambda I minus a equals 0. Across the diagonal, we put lambdas and multiply everything else by a negative. And here we are. So, the characteristic, oh, I'm sorry, we're not there yet. We're at this stage. And to find, you could pretty much use the shortcut if you want to find the determinant. You could pick a row or column. I don't know, probably let me use the shortcut. So the determinant of this will be positive lambda plus lambda plus lambda lambda cubed minus 1 minus 1 equal to 0. That's the shortcut. 3 lambda minus lambda cubed plus 2 equal to 0, or simply lambda cubed plus, negative lambda cubed plus 3 lambda plus 2 equal to 0, or lambda cubed minus 3 lambda plus 2 equal to 0. This is not quadratic, so I can't factor that by the traditional method. I have to use the factors of 2 divided by the factors of 1. Remember that one chapter back in the days when you took college algebra and you worked all of these out. So if I take 1 works. If I put 1 in there, I'll get, I messed up. If you change all the signs, that's a minus. So 1 doesn't work. 1 gives you a -4. -1. -1 gives you a -1 plus 3, or -1 works. So I have lambda plus 1 into lambda squared minus lambda minus 2 equals 0. That's lambda plus 1, lambda minus 2, and lambda plus 1 equals 0. So I get lambda equal -1 and 2. And now the tradition. If I take lambda equal -1, actually, let me add to myself more space. I'm solving -1, -1, -1, 0, -1, -1, -1, 0, and -1, -1, -1, 0. No need to really, we know what that is. If I take -row 1 plus row 2, put it in row 2, and take -row 1 plus row 3, put it in row 3, we know what's going to happen. I'm going to end up with that means x2 is free, x3 is free, x2 is free, and x1, if I move that to the right, is -x2 and -x3, which means corresponding to lambda equal -1, I have -1, 1, 0, and -1, 0, 1. Now, for lambda equal 2, if I put a 2 there, I'm looking at 2, -1, -1, 0, -1, 2, -1, 0, and -1, -1, 2, 0. And if I work this out, I'll be looking at, let me see, if I take 2 row 2 plus row 1 in row 1, and -row 2 plus row 3 in row 3. So if I multiply this by 2, -2 plus 2 is 0, 4 minus 1 is 3, and -2 plus 1 is 1, and that's a 0. And if I take negative that and add it to this, that's a 0, -3, that was -3, my mistake. You multiply this by 2, that's -2, plus a -1 is -3. Okay, they weren't adding up. And now if you multiply this by a negative, that's 1, that's a 3. Okay, there you go. They have to zero out. It doesn't work that they don't zero out. Oh, by the way, that was a -1, right? Okay, and now if I take row 2, add it to row 3, put the result in row 3, 2, -1, -1, 0, 0, 3, -1, 0, 0, 0, 0, 0. So here we have x3 is free. x2 is x2 is x3 as well, and 2 x1 equal x2, which is x3 plus x3, which is 2x3. So x1 is x3 as well. So lambda equal 2 correspond to the vector 1, 1, 1. Okay, now that we have enough practice on the following problem, we just want to find the eigenvalues. Eigenvectors will be the same work, just a bit busy, but we're not going to do that, even though this one works nicely, but 13 doesn't. So if I take the determinant of lambda I minus a equals 0, I'm looking at pretty much lambda minus 9, lambda plus 1, lambda minus 3, and lambda minus 7. Change all of these signs. Excuse me. And you notice this is a triangular matrix. So it's simply lambda minus 9, lambda plus 1, lambda minus 3, lambda minus 7 equals 0, or lambda equal 9, negative 1, 3, and 7. You could have just figured that out by looking at it. That turns out to be a really quick way of finding. Again, you're going to have 4 of those. That's some work, busy work, nothing more. Let's move the last problem up pretty quick. We look at number 16, t of x, y, z equal the following. Well, if we apply, so find the eigenvalues and the basis for each eigenspace of the linear operator defined by the stated formula. Suggestion, work with a standard matrix for the operation. Okay, well, if we take tx, where x is x, y, z, isn't that ax? Isn't that how those linear operators work? So basically, aren't you talking about nothing more than the x, 2, 1, negative 1, the y, negative 1, 0, and a 1, and negative 1, negative 1, 2. Isn't that matrix A? And now you know what to do. Take the determinant of lambda I minus A, set it equal to 0, and the process is the same. Let me work out this problem, even though it's a bit long, but it's okay. So what would that be? That would be the determinant of lambda minus 2, 1, 1, negative 1, 1, lambda 1, and negative 1, and lambda minus 2. I want that determinant to equal 0. So I could go ahead and say, you know what? And I'll get lambda times lambda minus 2 squared minus 1 minus plus 1 plus 1 minus lambda minus lambda plus 2 minus lambda plus 2. So I'm looking at lambda times lambda squared minus 4 lambda plus 4 plus 2 minus negative lambda plus 4 lambda cubed minus 4 lambda squared plus 4 lambda plus 2 plus lambda minus 4, and of course that equals 0. So I have lambda cubed minus 4 lambda squared plus 5 lambda minus 2 equals 0. Now, on this problem, I just want to make sure, so the last two, I just want to make sure you could find the eigenvalues. And this doesn't factor by traditional method. The factors are, possible factors are plus or minus. Factors of 2 divided by 1. So factors of 2 are 1 and 2. Divided by 1 are 1 and 2. Does 1 work? If you put 1, 5, 6, 1 works. Right? And you should try 1 again. Wait, that was cube squared. Yeah. Or you could factor it by hand. It doesn't matter, right? So I have lambda equal 1, and this is lambda minus 2 equals 0. So 1 and 2 are the only eigenvalues, and we know what to do from there. We come back to this matrix. A minus lambda I. We plug in the 1, figure out the eigenvalues, eigenvectors of those. Lambda equal 2. One of those is going to give you 2 vectors, and that's that. Well,